Evet.
Welcome to joint seminar number theory seminar series of Feza Gürsey Center for Physics and Mathematics, Harishchandra Institute in Allahabad, and IPM at Tehran. And today, Özge Ülkem will tell us about Drinfeld's elliptic sheaves and generalizations, as she is a postdoc at Academia Sinica in Taipei. We have time difference, so because of this, we have this unusual seminar time. But uh, at any rate, yeah, please, Özge. Yeah, thank you.
Thank you for the introduction and inviting me. Also, thank you for arranging the time a bit earlier. Otherwise, it was being very late for me. Uh, Today, I'll talk on Drinfeld's elliptic sheaves and generalizations. My talk will be mainly on four parts. First, I will make a brief introduction into function field setting, and then I'll talk and briefly define what's an elliptic sheaf and talk on some of its generalizations, mainly focusing on generalized D-elliptic sheaves. And then I'll state some results on the moduli spaces. And if time permits, I'll discuss the relation with elliptic sheaves and all the other structures with Drinfeld shtukas and other shtukas or other structures in the function field setting. So let's start. Maybe. No. So welcome to function field setting. So maybe you saw this before. Uh, Let me see. So this is, we have classical setting, which usually we worked in number theory. We start with the ring of integers, then we take field of fractions of it to obtain Q. Now we consider Q with usual absolute value on it, and then we take completion of Q with respect to this norm, and we get the real numbers. And then if we take algebraic closure of R, we obtain complex numbers. And at the end, we obtain algebraically closed complete curve, complete field, not curve yet, algebraically closed complete field. And that's our aim in the function field setting as well. But instead of Z, we start with FPT. The polynomial ring in variable t over fp, where here p is a prime. For now, I'll just state everything in the most basic setting, then we'll generalize. And we do a similar construction in this setting as in the classical setting. So first, let's take field of fractions of it. Now we consider this field with a norm defined, normalized such that the norm of t is p. This norm is usually denoted by p or even infinity. Now, different from the absolute value, this gives an non-Archimedean norm. Now, with respect to this non-Archimedean norm, we take completion, and we obtain the field of Lorentz series. And then we take algebraic closure of it, but since the norm is non-Archimedean, it's not necessarily complete, but we want at the end a complete algebraically closed field, so like we take one more completion. And this will be our setting. And we denote, sorry, okay, you can still see, great. Let's denote this. So we denote this field by C infinity, where you can think of infinity as 1 over t, and the polynomial ring will A. I keep recalling this setting during the talk, so and let me know if you have any questions. And one of the main objects in number theory and arithmetic geometry in the classical setting is elliptic curves over complex numbers. Now the question is, what's the analogy? What's the analog object in the function field setting? And it is defined by Drinfeld. They are called Drinfeld modules. So when first Drinfeld defined these objects, he called them actually elliptic modules because of the analogy. But nowadays we call them Drinfeld modules. So what's a Drinfeld module? A Drinfeld module of rank R is an FP algebra homomorphism phi from FPT to C infinity tau, where C infinity tau is set of polynomials, a non-commutative ring, with subject to this condition, where if you want to change elements, you change it with a twist. So that's why it's called sometimes twisted ring of polynomials. And a Drinfeld module of rank R is an FP algebra homomorphism from FPT to C infinity tau, and where T goes to such a polynomial like this, where Ci's are in C infinity and with CR non-zero. Here, there are a couple of things. First, since it's an FP algebra homomorphism and FPT is generated by 1 and T, as an FP algebra, it's enough to define, it's enough to determine where T goes. And it's rank R, so tau to the R we have, and CR is non-zero. Why this is a module? Because by this, so here is our construction, and by this construction, there is already an FPT module structure on C infinity. But by using this definition now, by using phi, we can define a new FPT module structure on C infinity, namely, for any C infinity, for any element in C infinity, we define one acts as identity, and T now acts by this polynomial. That's why we call them Drinfeld module. One example is, which is called Carlitz module. It is Drinfeld module of rank 1, where T goes to T plus tau. This is actually, so the first definition was given by Carlitz, but it was unrecognized due to the name of his papers. They are very generic, and they became, time passed without no one realizing this until Hayes, who was a student of Carlitz, and Hayes used Carlitz modules to give an explicit description of maximum abelian extension of function field. And later, so this Carlitz module is also related with Lubin-Tate formal groups and also the Drinfeld module. But neither Lubin-Tate nor Drinfeld was aware of Carlitz's work when they defined this. So it's really some time pass, but thanks to Drinfeld's modules are like generalizations of Carlitz modules, right? And this is how function field arithmetic started, actually. Drinfeld came along and defined these modules, and they were so nice that they indeed form an analog of elliptic curves in function field setting, and I'll talk on some of them here. So we already mentioned with Z, we have Z and FPT, the analogy. one might ask why the FPT is the right analog. Because the answer is because they have many similar algebraic properties. Like they are both PID, they both have finite unit rings, finite unit groups, finite quotient rings, finite unit groups, and more. And actually, Carlet showed that this analog actually goes beyond, but due to time, I'm unable to give all. But so when you talk about elliptic curve over C, we have this, it is given by this equation, right? AX plus B, where A and B are in C. And by using Weierstrass P function, one can actually interpret any elliptic curve as quotient of lattice. So it's enough to have an elliptic curve. It's enough to start with lambda as Z lattice of rank 2. And one can define exponential map. And moreover, we have such exact sequence where there is some missing, such an exact sequence. And moreover, thanks to this interpretation, this uniformization of elliptic curves, isogenies of elliptic curves are given by isogenies of lattices, which are homotopes of lattices, where here C is in C, and everything holds in function field setting as well, with some differences. So when Drinfeld defined this analogy, he indeed defined for, we can start with lattice, now FPT lattice of rank 2, and we can define exponential map, which gives us such an exact sequence, where now here, couple of difference, here we have this E, and it is surjective. We don't have the unit group here. It's always surjective. And isogenies are given by homotopes of lattices, where now C is in C infinity. Moreover, you can classify elliptic curves with more structures, but you can classify elliptic curves by using a Pralf plane. And we have also similar classification for Drinfeld modulus, where you can classify Drinfeld modulus with analog of a Pralf plane. This is called Drinfeld symmetric space, Drinfeld's a Pralf plane, or Drinfeld symmetric space, where this is defined as the projective space of R-1, C infinity, and then you get rid of all the K infinity rational hyperplanes. And why this is analog? This one see it's better when R is 2. When R is 2, you have C infinity minus P1 K infinity. This looks like P1C minus P1R, which is like upper and lower half plane. And we
What
can
is K
classify
infinity here?
Yeah.
What is K infinity here?
I can recall. Yes, you are right. So we had this, we started with FPT, and then we obtain the field. Then it is the field of Laurent series. Yes. And then we have C infinity, and this is K infinity. Thank you.
Thank you.
And there are actually more analogies. Like you have J invariant in both case, discriminant in both case. You have modular forms in both case. Let me add one more page here. Then we have here modular forms. It's coming a bit slowly. Can you see? Yeah. We have modular forms and we have Drinfeld modular forms. Now, I want to make a remark here, which involves this two issue. Namely, so this is two. We have only like rank 2 lattices because C is a field extension of R of degree 2. Whereas if you look at C infinity over K infinity, this is of infinite degree. So this allows us to define actually not just rank R lattices, but rank 2 lattices, but any rank R lattice in C infinity, which allows us to define Drinfeld modules of any rank. So when you talk about Drinfeld modular forms, one usually consider functions from holomorphic functions from omega 2 to C infinity, but that's just not it for us, right? So we can, because what about the holomorphic functions from C omega R to C infinity? And these are called higher Drinfeld modular forms of higher rank. And this is something that has no direct counterpart in the classical setting. So we can define, unlike classical setting, we can define modular forms of higher rank. Because of this extension allows us to define moduli space of Drinfeld modules of any rank. Now, this Drinfeld modular forms of higher rank is defined and extensively worked by Basson, Brauer, and Pink in their work. They defined it analytically and algebraically as well, and they gave many examples. And they also defined Hecke operators. But even though they really worked extensively, there are still many things to be worked out. And in our joint work with Özge, who is a postdoc in National Tsinghua University in Taiwan, we solved one of these open questions. This is Gezmiş, Ülkem, and we provide, I'm not gonna write the technical theorem, but let me explain what we did briefly. We provided a family of Drinfeld Hecke eigenforms of higher rank. And we use some determinant of twisted Eisenstein series and vectorial modular forms, and used vectorial modular forms, which is defined by Pellerin, but also Pellerin and Perkins. But anyway, if we go back to analogy, so this analogy is not just that, so, okay, we have modular forms, then we have Eisenstein series in both setting. We have modularity in both settings. We have uh, who knows, Iwasawa theory has been worked out, class field theory has been worked out in both worlds. And uh, Langlands correspondences is a big area that Drinfeld worked. We will come to that in a minute. Uh, but and there are also differences. One of the differences that, so for example, Riemann hypothesis is known in the function field setting for some time. And one idea is, how can we exchange these tools to the classical setting? I don't know how, but we will say a couple of things between these analogies in a minute. Yeah,
Can I ask a question? Do we have, for example, Shimura-Taniyama kind of result in the setting of Drinfeld, let's say in the Drinfeld universe?
yes, we do. It's for Drinfeld modular forms of rank 2, it's proved by Gepard-Böckle in his habilitation. It's, I believe, Euler-Shimura isomorphism. Is not as interesting as in the classical case because the representations that we attached are just one-dimensional. So it doesn't open a big area that it is opened in the classical setting. Like we don't have things as big images stuff in function field case because, well, the representations are quite obvious.
Oh, thank you.
So these are some analogies, and I'll try to make these analogies during my talk. So far we defined Drinfeld modules only in the case FPT, right, over the polynomial ring. But one can actually define Drinfeld modules in a more general setting. Namely, you can start with a smooth projective geometrically reducible curve over FQ, and you fix the closed point denoted by infinity, and A denote the ring of regular functions outside of infinity, and K is the function field of the curve, and L be an A field, which means you have a homomorphism from A to L. And in this setting, you can define a Drinfeld A module over L for any A and L, for any such A and L. And if you take Y to be just the projective line over FQ, then you obtain A to be FQT, and we are back to our case. But it can be defined in a more general setting. So this was the idea of Drinfeld, and this was the idea of Drinfeld to give analogues of elliptic curves, and then to work on Langlands conjectures, he gave another objects, categorically equivalent objects, which he defined the elliptic sheaves. So what are elliptic sheaf? An elliptic sheaf of rank R over an FQ scheme S. If you want, you can just take S to be spec FQ. There will be finitely many points, but it's still an FQ scheme. So anyway, an elliptic sheaf of rank R is a diagram of locally free sheaves over now Y times S, the fiber product. of y and s, such a diagram that has conditions on growth of these morphisms, of these arrows, and we have periodicity. This is rather technical idea. I avoid technical details here. These are quite specific conditions, but since they were too technical, I'm not gonna state them. But the idea is the following. So you want locally free sheaves over y times s, which means you want vector bundles over y times s. And to obtain an elliptic sheaf, you start with a vector bundle and you start modifying it around infinity, around this fixed closed point. But you don't want to modify too much or too small. So these conditions are there to guarantee us that we are modifying enough, just enough. And periodicity tells us that it's enough to modify only finitely many steps. And so that's an elliptic sheaf. When someone says elliptic sheaves, you can think of vector bundle with modification around infinity. And finitely many modifications. And if you forget the modifications, if you look at these locally free sheaves, vector bundles away from infinity, everything is just basically same. You have no new object. And that's how you pass from elliptic sheaf to Drinfeld module. You have an elliptic sheaf, which means you have a vector bundle and you are modifying. If you forget the modifications, if you look away from infinity, you just have a module. And that's it. So let's make an example.
Özge, by a modification, do you mean just passing from epsilon I to epsilon I n plus 1? Or I plus 1, sorry. So
yes.
What's a modification? It's these arrows you're calling them modifications.
Yeah, these are injective morphisms with satisfying certain conditions.
Okay.
Conditions on their co-kernel.
Okay, let's see the example.
Let's make an example. Maybe it will be better. So what we want locally free sheaves over y times s. And I would like to have of rank r. Right? So for simplicity, let's assume degree infinity is 1. Just for simplicity, everything holds for higher degree as well. So, but we want locally free sheaves over y times s. What's the most easy locally free sheaf over y times s? Just take the structure sheaf, right? And I want of rank r, so let's make it of rank r. Okay, I defined E0 to be this. And even, let's make it even simpler. Let's take S to be spec FQ. Then let's start modifying. Well, I want to modify around infinity. Okay, let's modify around infinity. So this is y times S, right? R copies of it. I start modifying from the first one, y times S or y times s r minus 1. And I define E1 to be this. And you can continue this until ER, which will be the case where everything is modified. Now you have these objects, time to define morphisms. How do you define these morphisms? you define it by the natural inclusion of y times s in here, right? And we take S to be spec of Q because then I want to consider this pullback with Frobenius. Then since S is FQ, then this behaves like identity so that I can define EI to EI plus 1 to be as just JIs. Let's call them JIs. And there you have it. This is an example of elliptic sheaf of rank R. But this was the idea of Drinfeld, that to show that these are categorically equivalent with Drinfeld modules is some work. And by using this dictionary with some class field theory and elliptic cohomology of the moduli space of elliptic sheaves, Drinfeld proved this Langlands conjectures for GL2. Yeah. And since then, many generalizations of elliptic sheaves have been worked out. So here are some more analogy with and some generalization of elliptic sheaves. So in classical setting, we have modular curve, which is like moduli space of elliptic curves, right? And in function field setting, it corresponds to Drinfeld moduli varieties, which is just moduli of elliptic sheaves, or equivalently moduli of Drinfeld modules. Then in classical setting, you can also think modular curve as like a quotient of a Pratt plane with suitable group. And Hilbert modular varieties you can think of them as, now you have copies of a Pratt plane and you look at quotients of it. And the analog of Hilbert modular varieties in function field setting is moduli of Frobenius sheaves, which can be taught in a similar way, where for Drinfeld moduli varieties, you can think of them as, okay. You can think of them as the quotient of Drinfeld Pratt plane. Now, moduli of Frobenius sheaves, which is defined by Stuhler, you just look at the product copies of a Pratt plane and you take quotient by a suitable group. You have Shimura curves over Q, which again you have a Pratt plane. Now you have gamma, but it includes some quaternion algebra. It's some related with quaternion algebra. And it corresponds to moduli of D-elliptic sheaves in the function field setting. Here, D is a maximal order of a division algebra. And you can think of them again as omega R, suitable subgroup, but with D included now. Now then, what's the Shimura varieties to attach to inner forms of GL2 that split at all infinite places? What's the analog? And the answer is given in my thesis. This is what I called generalized D-elliptic sheaves. And so so far we started with Drinfeld modules, which are categorically equivalent to elliptic sheaves. Then you have two generalizations which are non-related. Frobenius-Hecke sheaves defined by Stuhler and D-elliptic sheaves defined by Lamon, Rappaport, and Stuhler, where D-elliptic sheaves can be thought as elliptic sheaves with the action on them. So you have these vector bundles still with modifications around infinity, but now your vector bundles has order of a division algebra action. And you get a D-elliptic sheaf. For Frobenius-Hecke sheaf case, instead of one infinity, you have many infinities. But again, you have vector bundle. Now you are modifying around many infinities. Then if you put these together in a way, you have generalized D-elliptic sheaves. So let's talk a bit on generalized D-elliptic sheaves. So let's fix our setting.
Before that, can I ask a question? So,
Yeah.
for example, in this dictionary, we have analog of Hilbert modular varieties in the FF setting and so on. Do we have analog of Ziegel modular varieties?
Well, not yet, not that much. Even the thing is, even the Frobenius-Hecke sheaves are not greatly worked yet.
I see. Okay,
So so here there is a work in classical setting. There is a work of Hilbert modular forms, right?
right.
But in function field setting, it is not yet defined. We are working on it, joint with work in progress. With Yansun Chen and Özge is to define Drinfeld-Hilbert modular forms.
Is there
And
motif theory also? I mean, can we attach some sort of motives for these things, for these objects?
sorry, I couldn't hear. Can we attach
Uh,
what?
Motives, like pure motives or something
Yeah,
like that.
yeah, we can.
Okay. Yeah. Yeah.
I'll come to that at the end
Okay.
as a
Thank you.
summary. But here, to define Drinfeld-Hilbert modular forms are not that immediate. Again, one of the difference is in classical setting, there is Peterson's inner product, right? We don't have it. And that has some problems. That gives us some problems. Hopefully I can give another talk on Drinfeld-Hilbert modular forms soon. So let's talk a bit on generalized D-elliptic sheaves. So far for Drinfeld modules and elliptic sheaves, D-elliptic sheaves, we had one curve and one infinity. And then first Stuhler came and asked, okay, what about if I take a finite covering of this curve so that this splits completely, this infinity splits completely. And then he worked over here. So that's what I mean when you have Frobenius-Hecke sheaves, you need to modify around many infinities because you have h many infinities here. And so here D is an Azumaya algebra, but you can just take D to be the matrix algebra over X. And we assume that around infinity, this D actually just matrix algebra. This is the local objects completed local ring around each infinity. and we take S to be FQ scheme, and sigma is again an related Frobenius on X times S to X times S, defined as identity on X and Frobenius on S. Now here we need to fix one closed subscheme of this fiber, one closed subscheme S prime of this fiber product, which is called the characteristic, and we need it for later. By using this characteristic, we will define a stack over Y. We will push it down. And for simplicity, we assume degree infinity is 1. Again, a generalized D-elliptic sheaf is a diagram of locally free sheaves over S over X times S, such a diagram which has conditions on the growth of the arrows of the morphisms, and we have periodicity. Here, one difference is that we have I underline. It is I1 IH, an element of Z to the H instead of Z. And you can think of it as each in this correspond to each infinity above. Now we are lying above. We have not just one infinity, but many infinities. But the idea is same. You have vector bundle, and you start modifying around not just this one fixed point, but many infinities. But you don't want to modify too much or too small, so that you have these conditions on their co-kernel. And its periodicity tells us that it's enough to modify only finitely many times. Here, I want to specify one thing. One condition one of these conditions on the growth is on co-kernel of these T, let's say Ti's. And this has support on this image of this psi here. Yeah, this we need it for other theories, but do I have time? Okay, let's just pass a bit. Why I call them generalized elliptic sheaves is because if we forget that we have a covering, then a generalized elliptic sheaf is nothing but D-elliptic sheaf defined by Lamont, Rappaport, and Stuhler. And if you forget the D action, you still have covering, but you forget the D action, then you have Frobenius-Hecke sheaves of Stuhler. But okay, we define these objects, then let's look at their stack, right? I want to classify these objects. But if I just look at it purely, then it's too big. So as in the case of abelian varieties, let's put some level structures on them, which we can define levelized structures for I being nice finite closed subscheme of X. Then we obtain the stack of generalized elliptic sheaves with levelized structure. But what I want to do is I want to uniformize this moduli stack over the fiber over infinity, right? So we had this xy so that this infinity splits completely. This is of degree h. But right now, even with level structure, this is a stack over x. But I want to push it down because I want to uniformize it along the fiber over infinity, which lies below. So to obtain this, we put a condition on the characteristic. So we are putting a condition on the this growth of the morphisms, of the modifications, condition on the modifications, so that we can obtain a stack. Now this is a stack over Y. And okay, then what are these? Now, first theorem is that this stack is actually a Dellin-Mumford stack, which is smooth over Y, and we get rid of the bad points, which there are only finitely many. And moreover, if I consider it with non-trivial level structure, then it is a scheme. So at the end, I have a moduli scheme with non-trivial level structure. Then great. So let's consider modular curve, which can be thought of as moduli scheme of certain elliptic curves, but it has cusps, right? It jumps, points jumps, and you need to put them back by compactification. But thanks to the D action that I have, the points on my moduli scheme cannot jump far away. So I already have a compact space, which the second theorem tells us that this stack over Y is actually is proper. So this D action keeps points in order that they can't jump far away. So I don't need to compactify, which has its upsides and downsides. One good point is that I don't need to compactify, right? I don't need this process. But on the other hand, I don't have cusps, so Fourier series doesn't come very naturally then. So when you define modular forms, the first example is usually Eisenstein series, but then in our case, it needs more work. So, okay, then let's uniformize this nice compact moduli scheme along the fiber over infinity. Great. This is another theorem in my thesis, and we have isomorphism of formal schemes over this formal scheme over affine formal scheme, SPF, or O infinity, where here AF is the others, and HI is open compact subgroup of this star of others. It's related with level structure, and HI only acts on the others, and D star acts on both. And we have here H copies of this omega hat, which is the formal completion of the Drinfeld upper half plane, because I have H many infinities. This is like complex uniformization of Shimura curves, Shimura varieties, because I don't have a uniformizable locus, which would be the case of p-adic uniformization. But in my case, everything is uniformizable. So it can be thought of as analog of complex uniformization. Okay, so one application is a special case when you forget the covering, which means we only have the D-elliptic sheaves. Then this theorem gives us a uniformization of D-elliptic sheaves with level structure, which is only stated in Bloom-Stuhler, but without a proof. So I provided such a proof. But as an application on this, we use this uniformization theorem for D-elliptic sheaf to define cycles on Hecke correspondences associated to the moduli space of D-elliptic sheaves. So on L, on the moduli space of D-elliptic sheaves, one can define Hecke, we have Hecke correspondences. Then this is a joint work with Fusun Wei, and by using the Hecke correspondences and this uniformization theorem, we define cycles. These are cycles on the moduli scheme. And then we look at their intersection number, and we related this intersection number with modified Hurwitz class number. So this can be thought of as this is like similar to the Kronecker-Hurwitz class number relation. Hurwitz class number relation. Or more generally, there is this phenomenon which relates class numbers with intersection numbers, right? Then not just Kronecker-Hurwitz, but there is also work of Hirzebruch-Zagier for Hilbert modular varieties of associated to real quadratic fields. And our work is similar to theirs. We don't have the Hurwitz class number. We have modified Hurwitz class number. Okay, I don't have much time, but I had some more analogies, but I want to talk a bit on shtukas. Like 2 minutes, I want to talk on the shtukas. So we had Drinfeld modules, which are categorically equivalent to elliptic sheaves, which were such diagram, right? Diagram of vector bundles, modifications around infinities. And if you just look at one triangle in this, here, one triangle in this diagram, you have shtuka. Since there are many shtukas now, we call them Drinfeld shtuka. And this is actually what Scholze got the idea to define this p-adic shtukas. His aim was to define this shtukas, Drinfeld shtukas, in classical setting, and had the work through. And we have such objects in every case. So for D-elliptic sheaves, this is the module site called Drinfeld Stuhler OD modules. First, this is mentioned in Lamon Rapport Stuhler, then worked by Tellman as well, and recently by Papikian. And on the shtuka side, we have D shtukas. I believe they were defined by Lamon, but I have to.
Can I ask one question? Drinfeld shtuka is a local object in characteristic P?
In function
Yeah,
field setting.
I mean, is it
Yeah,
local object or global? I mean,
they are global.
they are global. I see. No, because I mean,
They are, again, everything is same. EIs are still locally free sheaves over Y times S.
okay,
You have one curve, one infinity, and S is an FQ scheme.
I see.
Also local shtukas.
I mean, because you mentioned that Scholze tried to define shtukas for QP, right?
Yeah,
Did he use there the local version of Drinfeld shtukas? Maybe he used this tilting correspondence from characteristic P to characteristic 0 kind of thing. It's perfectoid theory, maybe. I mean, just
maybe.
because of
Yeah,
that.
but
Okay, yeah.
I have to recall what Scholze did.
Okay,
But
yeah.
these are global objects, but we have also local shtukas, which are like Dieudonné modules.
And of course, probably they are related with this Drinfeld shtuka, right? Local
Yeah.
ones. Yeah, okay.
And Laforgue as well, I believe. So for generalized D-elliptic sheaves, it's pretty new. So this is, I have to say, work in progress, which I'm working on it. Generalized Drinfeld-Stuhler OD modules. And here, well, one can define generalized D shtukas. This is not the Laws one, not the Laws objects. Let me make law defined already a generalized D shtuka, which they are not equivalent. So, but one can define associated generalized D shtukas, which we did, but the more interesting, maybe more interesting case is that this is work in progress and joint with Gepard-Böckle, is that we claim that our generalized D-elliptic sheaves are equivalent to G shtukas, which are first defined by Aristeh and Hartel, sorry. But recently, Hartel and Shu had a even more general case of G shtukas. Usually, Aristeh and Hartel assume that G is parahoric group scheme associated to in the sense of Brohat-Tits. But in their recent preprint, Hartel and Shu doesn't have this condition. G is, again, they have some conditions on G, but not necessarily parahoric. So even more general. And we claim that when G is the Weyl restriction of the unit group, well, there is a scheme associated to it following Brohat-Tits. And if you consider its Weyl restriction, you will obtain a nice group scheme. And we claim that this is still work in progress and joint work with Gepard-Böckle, that they are equivalent to G shtukas. That's all I want to say. Thank you for your interest.
Thank you very much. Any questions or comments?
I have a question.
Yeah.
You talked about many infinities, some infinities. What does it mean? I mean, different infinities should we understand?
Different infinities. Let me go back to setting. Yeah, here. So we consider this, we start with, okay, we have one curve and one infinity, right? Then we look at finite covering of this curve of degree h, so that this infinity splits completely. So these infinities are different places. But since it splits completely, if you look locally around each infinity, it looks like you are looking around infinity below a bit.
What kind of object is this infinity and infinity I? Infinity Y?
They're absolute value. Just think like absolute value.
Absolute
Oh yeah,
value.
you can think of absolute values.
Okay, thank you very much.
Can I ask one question?
Yeah.
So there is something called Anderson motif.
Yeah.
I mean, Greg Anderson worked on these things also. Are they related or what?
They are related. They are, so what Anderson did states, it maybe lies here, that so we have Drinfeld modules, right? Then Anderson defined T module. T modules and T motives. And they are like they are like higher dimensional generalization of Drinfeld modules, in the sense that abelian varieties can be thought of as higher dimensional generalization of elliptic curves. So then this is, I believe Hartel has some work on it, that this should be what is called abelian sheaves. There is work of Hartel Sin, I believe, Hartel Bornhofen. It started, I know it from Hartel's paper on uniformization of abelian sheaves, which I also followed to prove the uniformization theorem in my thesis.
Thank you. By the way, Özge, let me tell you that in your last slide, when you mentioned Araste is one of the listeners here, by the way, now.
Ah,
Yeah.
hi.
Hi. Okay, thanks. Just so I also have some questions.
Yeah.
Yeah. So at some point you mentioned that your generalized elliptic sheaves, the moduli space, is Mumford and smooth. And I guess, I mean, this smoothness, you have like, I mean, sort of assumptions on the boundedness condition, on the modification you are imposing. Elsewise, I do not expect that you would get something smooth.
Oh, but
Like, I mean,
that's
there
why
should be some
now this
like
is
minuscule sort of
it is
assumptions on
smooth.
that.
Yeah, it is in this smooth,
Yeah.
but this is a
Mhm.
stack over y, not x. So I have one infinity.
Mhm.
Even though still my objects, to obtain my objects, I have modifications around many infinities, but with this condition on the characteristic, I get a stack over y. So I don't know if, like, without this, if I consider the stack without this condition and get this stack just g d I, which is a stack over x minus, let's get rid of the bad points. I don't know if this is smooth or not.
Yeah, I mean, it depends to the type of modification you take. So it depends on the boundedness condition you impose. I mean, as far as I understand, I mean, smoothness is like matter of taking minuscule boundedness conditions.
Sorry, I
something like
couldn't
that.
understand
So
your
this is
last
something that
sentence.
makes me a bit confused. So I think the smoothness comes from sort of boundedness condition you're imposing to modify these.
Sorry, I think
Is
the
that it?
internet is not very nice. I can't hear you smoothly, but let me just say, for smoothness, I used a theorem that I saw in Lamont, where you have this diagrams of stacks. I don't remember the conditions now, and I over FQ. I believe, or over y. But I refer it in my thesis where I took the diagram, and I put my stack in such a nice diagram and drive the smoothness from there. I don't know if this was what you are asking.
I mean, at least I have like this sort of feeling that you're like taking certain sort of modifications, not like, I mean, general sort of modifications.
Mhm.
It looks to me that the boundedness condition you are taking care of is kind of minuscule ones,
Ah,
but I
as the
can't see that.
bound.
I mean,
Yes, it should be minuscule ones. And yeah, it should be the minuscule ones. And even
I
I
mean, else
believe
why you
it's
would
even
put
about
some sort of
maybe
similar.
100.
Yeah, I mean, that was the point.
Mhm.
Okay,
Okay.
I have like one little comment. So the G shtukas we are constructing with URSS, so they are for general flat affine group scheme over C. But when we are in, like going toward uniformization theory and that sort of things, then we have to like assume that the generic fiber is like, and then the special fiber is connected. So the parabolic type things not from the construction. And then there is one further comment. So in that work, so they are the characteristic sections come together at the infinity. So this is not matter of the group G, but it's like matter of intersecting characteristic sections. That's
Intersection of what?
Uniformization theory of the characteristic section. Yeah. So it's not like matter of the group, but it's like matter of characteristic section. So they call it at infinity, and then like they have like a method using the global boundedness conditions rather the local boundedness condition to treat. Yeah. Okay, thank you very much.
Thank you.